Welcome to our video on glycogen synthesis. So in this video, we're going to look at the enzymes associated with glycogen synthesis and then the reciprocal regulation of glycogen synthesis and degradation. All right, so if we take a look at our metabolic map here, we are now going to be talking about this kind of pathway here. All right, and so we're really going to be taking a look at mainly this piece of it. So when we look at this, scroll back in, here we go. I know there's a lot of stuff on this slide. Let's just take a look at it one step at a time. So first of all, note that glycogen is synthesized and degraded by slightly different pathways, and you see that in this highlighted section here. Okay, so when we degrade it, we're going directly from the glycogen to the glucose 1-phosphate, but when we create it, we are stepping through this thing that we're going to call UDP glucose. So let's take a look at that. Over here we have our uridine diphosphate glucose. So this is a pyrimidine base instead of purine base, so it has a single ring. Here's our base rather than that double ring. Okay, we've got our ribose, and then we see our 2 phosphates, and then it's got a glucose bound right in here. If we look at synthesis versus degradation, right? So in degradation, we were creating our glycogen. We were using phosphate to split apart and break off one glucose 1-phosphate, and then we had our glycogen left over, the rest of it. For synthesis now, we're going to add on, right? We're going from glycogen with N units to N+1. But we're going to go through this UDP glucose to add that. All right, if we look at this process, okay, we have glucose 1-phosphate right here. We have our UTP with the triphosphate. So notice 3 phosphates here. All right, and we're breaking off 2 of them. So we're breaking off this pyrophosphate, these 2 phosphates that are bound together right here. Okay, to give us our UDP glucose. Now, interestingly, if you take a look, notice that we have double arrows here. This is a reversible reaction. It's not heavily energetically favored to go forward as opposed into the reverse. The driving force for this reaction, what really pulls it towards the products, is the fact that that pyrophosphate is readily hydrolyzed to split apart into 2 phosphates. And when that happens, okay, this process that is very energetically favorable pulls this product out. So think Le Chatelier's principle. The fact that this bottom reaction readily occurs uses up this product from the first reaction and pulls this whole reaction to the right. Okay, so it sets us up with this high energy bond. This UDP glucose has this high energy bond to glucose that's going to allow us to form this biosynthesis, to add on to our glycogen. And just as a highlight, this is the little piece we're talking about here, right? Going from glucose 1-phosphate to that UDP glucose. All right, so glycogen synthase is our enzyme, and it catalyzes the transfer of glucose from that UDP glucose to a growing chain in our glycogen. All right, so let's talk through this, and then we're going to look at a lot of pictures, okay? So glycogen synthase is the key regulatory enzyme in glycogen synthesis. and it transfers a glucose to the C4 terminal residue of a glycogen chain. And it can really only form 1,4 glycosidic bonds. So it can form those alpha 1,4 bonds. Remember, glycogen is branched. We're going to take a look at that, but this glycogen synthase really only helps us build that straight chain. And it needs a starting point. Okay, it's got to have a starting point as like a primer. And so that starting point is really provided by this small protein called glycogenin. And it in itself is an enzyme that can get the polymer unit started by making a chain about 10 units long. Okay, and once that core is started, then the synthase can take over and extend it. This is actually a homodimer, the glycogenin, so if we think about it, right, I'd have a starting piece here, and it'll be a homodimer. There'll be two of them, right? And it will set up this starting chain of these glucose on and on to about 10 to 20 units long. And then the glycogen synthase is going to take over. If we look at a cross section, right here is that little G protein we were talking about in the middle, and it gets us started with a branch. And you can just see on this that there is a lot of branching in our glycogen. So let's look how that branching forms. So we have our core, that glycogenin, and it starts building out. So each of these little hexagons is a glucose unit. And that core builds out about 10 units. And then that glycogen synthase can start adding onto it. Okay, so you can see it starts building on. Each of these is coming off one of those activated glucose molecules, those UDP glucose. They come off one at a time. They're bound to our glycogen. Now that glycogen synthase, right, is building just those alpha 1,4 linkages. Okay, they're adding them to the non-anomeric carbon side of this branch. So we're going to keep adding on this side. But it can't make the branching. And so what happens is that we also have what we call a branching enzyme. And what that branching enzyme does is it cleaves those alpha 1,4 linkages. So it cleaves the alpha 1,4 linkages. And it will cleave them only if we have a branching enzyme. It only works if it's at least 11 units long. So this whole chain would need to be at least 11 units long before that branching enzyme will start to work. And it'll typically clip off about 7 to 8 glucose units. Clips off 7 to 8 units. Okay, 7 to 8 of those monomers, but still stuck together in a chain. Okay, and then it will come back and add them back on an earlier piece using an alpha 1,6 linkage. That new branch must be at least 4 residues from any previous branch point. Okay, so the synthase adds to the non-reducing ends. That's not what I wanted. Adds to non-reducing ends and builds the straight chain. The branching enzyme over here comes in and cleaves off about 7 to 8 units and pulls them back and adds them with that alpha 1,6. So you end up getting a branch around every about 10 to 12 glucose residues. So branch around every So there's a lot of branching. Okay, these are really the only two enzymes we're going to need to keep track of here, this glycogen synthase and the branching enzyme. So let's talk about regulation. Glycogen synthase has both a phosphorylated and an unphosphorylated form. Notice that this is opposite the degradation pathway, and we'll talk about the importance of that. Okay, but that the phosphorylated form is usually, let's actually change the color of that. The phosphorylated form is usually inactive. The unphosphorylated form is active. That is opposite the glycogen phosphorylase we looked at the previous videos. It also has different conformations. Okay, the T form that is less active, the R form that is more active. So regulatory processes, we can have allosteric regulation. So the glucose 6-phosphate can bind allosterically to some point, and when it does, it converts. So this is a positive effector, because notice it converts that T form to the R form. It converts us from the less active form to the more active form. And it turns out that this conformational change favors dephosphorylation. So go back up here, unphosphorylated, more active. So as this changes form, it makes it easier for this enzyme we're going to look at, protein phosphatase, to pull off those phosphate units. All right, so allosteric regulation, glucose 6-phosphate, positive effector, changes conformation to make it easier to pull off the phosphates. Then covalent regulation is adding or taking off or adding those phosphates. Insulin will promote dephosphorylation, so insulin will make it more active. Makes sense, right? If you have a lot of glucose, it'd be great to store some of it up as glycogen. We would like this synthase to be active. Glucagon and epinephrine, we've seen those before, right? Promote phosphorylation. Also makes sense. Think about it. Adrenaline, epinephrine. You are being chased by a bear. You need immediate energy. You don't want to be using time and energy storing up your glucose. You want to be using this stuff for energy. You want to be breaking down that glycogen instead of building it. Okay? So those are going to be our covalent regulation pieces. All right. So let's compare. Glycogen breakdown, phosphorylase was the regulatory enzyme, and it was most active when phosphorylated. In glycogen synthesis, glycogen synthase is the regulatory enzyme, and now it's going to be inactive when phosphorylated. And so let's think about why is the fact that phosphorylation has opposite effects on glycogen synthesis and breakdown advantageous. If you think about that, when the signal comes to say turn on the kinases, and we're about to look at a picture of that, okay, and review that, that when that signal comes, say the epinephrine, activates our G protein, and we activate those kinases, they can phosphorylate serines and threonines all across enzymes in the cell. So they can, that same signal can now cause it to phosphorylate both the phosphorylase, which activates it, and the synthase, which deactivates it. So if you think about that phosphate on-off switch, we certainly don't want to be both breaking down glycogen and forming glycogen at the same time. That's a waste of effort. We want to be doing whichever one we need at the moment. So this fact that the same process has opposite effect aids in our reciprocal regulation. So let's take a look. There's a lot of stuff on here, but we're going to look at it step by step. So coordinate control of glycogen metabolism. We've looked at this picture several times, right? Here's our glucagon or epinephrine binding and setting off our cascade. This protein opens up, the GTP floats out, GTP floats in, which causes this to break. It comes over here. It activates that adenylate cyclase, which makes the cyclic AMP, which activates the protein kinase. Now, when we look at that, that can phosphorylate the phosphorylase kinase, which phosphorylates the phosphorylase, which aided in breakdown. So when this all happens, it's helping us break down glycogen. Now, if we're breaking down glycogen, we certainly don't want to be building glycogen. And nicely, this same protein kinase also phosphorylates the glycogen synthase. But notice the pink are all inactive, the green are active. Glycogen synthase is inactive, okay, when it's phosphorylated. So as we activate dephosphorylation, as we activate our glycogen degradation, we're deactivating the synthase. We'll look at this in just a minute, glycogen synthase kinase. Let's take a look at this. So let's say this happened, okay? You have a scare, you make some adrenaline, you start this whole thing, you're breaking down your glycogen, you are not synthesizing new glycogen, but at some point, we want to change that, right? At some point, you're no longer being chased by a wild animal, you're no longer frightened by whatever it was. You've maybe eaten a meal, you've got a ton of glucose. Anyway, whatever it is, we want to slow that degradation process and speed our synthesis. This protein phosphatase 1, okay, PP1 here, so how we sometimes abbreviate that, is going to reverse those kinases. So think about it. Kinase adds phosphates, so the protein phosphatase 1 is removing those. It's reversing the effect of those kinases. All right, so if we, let's see, want to look at the effect of the protein phosphatase 1, over here, as it pulls phosphates off of the phosphorylase kinase and the phosphorylase A, it deactivates them and slows glycogen degradation. Let's come back up here. So remember that that was right here and right here. Those were the things that caused us to break down the glycogen. So we are deactivating the one that directly breaks down the glycogen. And we certainly, if we're deactivating that, we don't want to keep reactivating it. That would be a waste of effort. So we pull phosphates off both of those and slow that degradation process. At the same time, we're going to take the phosphate off of the synthase, but that has the opposite effect. As we take the phosphate group off, it converts it in a more active form, and so we stimulate the formation of glycogen. All right, so when we have plenty of glucose to be stored, we're going to activate this protein phosphatase. Okay, and it's going to dephosphorylate all three of these, right? The phosphorylase kinase, the phosphorylase, and the glycogen synthase. For two of them, it deactivates it. For the third one, it activates it and allows us to store that glucose. Or I'm sorry, that glucose as glycogen. All right, insulin is also important in these regulatory pathways, and we're going to look at that with this piece I said we'd come back to. Glycogen synthase kinase, which is something else that phosphorylates and inhibits the synthase. So let's just remember that when we phosphorylate the synthase, right, it's inhibited. It is less, it is not going to form glycogen. So let's look at the process here. So glycogen synthase kinase, we've got our insulin here. It sets off a cascade, this protein kinase. And then here is the piece we are looking at, okay, this glycogen synthase kinase. And notice that when it is phosphorylated, well, sorry, we're looking at this, okay, we're setting off this glycogen synthase kinase. And it is an enzyme. Let me erase what I just did. Let's look at the bottom part first. Glycogen synthase kinase is an enzyme that adds a phosphate to glycogen synthase. Let's just make a note. So this is an enzyme that adds a phosphate to glycogen synthase, hence the term, or hence the name, right? Glycogen synthase kinase. So it's adding a phosphate. If you think about it, when we have lots of insulin, do we have lots of glucose in our blood or not a lot? We have a lot of glucose. So if we have a lot of insulin, we want to be building our glycogen. So when we have lots of insulin, we want glycogen synthase to be active, which we know is the dephosphorylated piece. Well, glycogen synthase kinase is going to phosphorylate it. It's going to make it inactive. So we do not want this active. Okay? And so when we have lots of insulin, we are stimulating these protein kinases that are phosphorylating the glycogen synthase kinase, but we can see that it is inactive when phosphorylated. So we're essentially turning it off with the insulin, which is good because when it's active, it's turning off our synthase, and we don't want that. Okay, we want the glycogen synthase to be active and move the glucose into that storage form. All right, let's think about a problem. Okay, imagine yourself as a medical student trying to get research experience. The attending physician has a patient with a liver disorder that might be due to a defect in glycogen metabolism. Okay, so we're looking for a potential defect in glycogen metabolism. She gives you a sample of the patient's glycogen and tells you to incubate that sample in a test tube with orthophosphate, so just that phosphate, phosphorylase, transferase, and debranching enzyme. If you think about where we've seen those, we have seen those in glycogen degradation. Those were our enzymes for glycogen degradation. When you do that, you find that the ratio of glucose 1-phosphate to glucose formed is about 100, right? So we are getting 100 glucose 1-phosphate for every phosphate for every 1 glucose. You get the idea. And we want to see, here's our question, right, is what do we tell the physician? What is the possible enzymatic deficiency in the patient? Right, so to do this, you're going to have to think through what we know about synthesis and degradation. So here are the 3 enzymes we added, right? We've got phosphorylase, our transferase, and that alpha-1,6, here we are, glucosidase, right? We have our debranching, our transferase, and our phosphorylase. And we collect data on how much glucose 1,6-phosphate we have and how much glucose we have. All right, let's think about when we make these. We make the glucose 1,6-phosphate when break the straight chain, right? So those alpha-1,4 linkages. We make glucose when we break that branching point. Our alpha-1,6 linkages. If you think back to what we said that we get a branch, right? We expect that these branches form every 10 to 12 monomer units. So when you think about a 100-to-1 ratio, is that too high or too low? It's too high, right? Because we shouldn't have 100 times of these. We should have about 12 times, 10 to 12. So that says that as this patient is making their glycogen, they are not effectively branching it. Okay, there is probably something wrong with this branching enzyme, all right, that is not creating as many branches as it should. So to answer this question, you needed to have a working knowledge of kind of the pathways and the functions of both pieces. Degradation, the last 2 videos, synthesis, this video. All right, and so you need to think about those. You also need to be able to think about, not with this problem as much, but the regulation, the allosteric and phosphorylation effects, and how these things are reciprocally regulated. All right, that is it for glycogen synthase.